Today, I shall discuss the velocity diagram of steam turbine. Of steam turbine. How to make velocity diagram and what is its application? Okay. Now, first of all, I am drawing a blade of steam turbine. Okay. The shaft is in this direction and it rotating in the perpendicular direction with this page. So this direction of this blade will be this because it's rotating in this direction, and this velocity is represented by Vb. Okay, now as we know, this blade is rotating and the steam is entering through this direction. This is inlet and this is outlet. So as the steam is entering through inlet direction and the blade is rotating, obviously the velocity which is entering to this blade must be relative velocity. So this relative velocity will be in the tangential direction to this blade, which is entering to this blade and going out. Now the steam direction, which is relative velocity, which is represented by Vr1. This Vr1 is the relative velocity. Okay, at inlet. Okay, now this velocity is Vb. If we draw a parallel line at the end of this relative velocity, that is direction of this relative velocity is this, and if we represent this relative velocity, this blade velocity with this relative velocity, then this at this point we have to draw a parallel line with same length, parallel line with the same length of Vb. Then this is the Vb, which is Vb. Now connect these 2 points, end point, and produce a triangle. This triangle, and as you know, this the triangle having the direction. So if it is resultant of these two velocity, then this resultant velocity direction will be the opposite, because continuously the direction is showing upward and the rightward, so the direction is like that, but this direction will be the opposite. So this is the opposite direction, and this velocity is called v1. This is absolute velocity. This v1 is absolute velocity at inlet. Okay. Now this triangle is called inlet triangle of the blade. Now further I am drawing this same diagram here. This will be the blade, this is the relative velocity, Vr1, and this is the blade velocity Vb, and make this triangle. Obviously this direction is the upward, this is the same direction, and this will be the opposite direction, and this is v1. Now make the outlet triangle. As you know, the tangential direction, this is the tangent, and this tangential direction with this line is the relative velocity. Similarly for this outlet, this will be the tangent with this line, and this is called VR2. Now this is the VB. We draw a parallel line with this VB at the end of this outlet of relative velocity. So this is the parallel with this VB, and this direction will be the same direction of this line. Now this is VB, and connect these 2 points. We got the line having the opposite direction for resultant. As we have produced the resultant of these two velocity, this resultant velocity having the opposite direction, because this direction is in this direction directed, and this direction in the same direction from this point. Now this will be the opposite. This is resultant, and this resultant velocity is the V2. Okay, now this line is the V2. Now we got this outlet triangle. And this is the inlet triangle. This is outlet triangle, and this is inlet triangle. Now produce the velocity diagram. Velocity diagram. Now, as you know, this inlet and outlet triangle having the same velocity, which is VB. You can see here VB, and an outlet triangle, this VB also present here. So we can superimpose the inlet and outlet triangle to produce the velocity diagram. So velocity diagram is produced by superimposing the inlet and outlet triangle. Now how we can superimpose the inlet and outlet triangle? You can see that the VB is common. So first draw the VB, which is VB. You can see this VB, this is VB. Now first of all, you draw the inlet triangle with this line. So this is the inlet triangle. Okay, you can see here, this is VR1, this direction is this, and this is V1. Similarly, we can draw this outlet triangle with the same line. So represent this line, and you can see that this is V2. So this is V2, and this line is VR2. You can see this triangle is represented here, as you know, and the direction will be this. This is the velocity diagram, but you have to produce another two velocity in the velocity in this diagram, which is VW1 and F1 with VW2 and VF2. Now you know the absolute velocity is this. Now make the two component of V1, which is tangential, this tangential direction, this is the tangential direction, this is the tangential direction, and this is the axial direction. This is the axial direction. So if we make this V1 in the tangential direction, then just increase it, connect it, so you can got in the tangential direction is this one. So total velocity is along the tangential direction is Vw1, and the axial direction, this is the axial direction, this is axial direction, this is a tangent axial direction. Now axial direction, this velocity of this component of this v1 is vf1. Similarly, for outlet triangle, this is the absolute velocity at the outlet. Now we can mate the two component of v2. The tangential direction component of this v2 is called the vw2, and the axial direction is vf2, where vw1 is whirl velocity at inlet, vf1 is flow velocity at outlet. And similarly, vw2 and vf2, this is whirl velocity at outlet, and this vf2 is the flow velocity at outlet. Okay. Now this angle is called alpha, which is the nozzle angle. This alpha is nozzle angle. This is the blade inlet angle theta, and the blade outlet angle phi, and this is the beta. This alpha is called nozzle angle or guide vane angle. This theta is the blade inlet angle. Phi, the blade outlet angle. And beta is the fluid flow exit angle. And this is the velocity diagram. Now you can see that for this velocity diagram, if we know v1 and alpha, then we can produce another data of the inlet triangle, that is vw1, vf1, vr1, theta, etc. Similarly, if we know the vb, this is the vb, this is vb, then we can easily produce the outlet triangle data, that is vr2, v2, vw2, theta, this is phi, everything from the inlet triangle.